Okay, good morning, everyone. I make that 10 a.m., so let's make a start. Welcome to the revision session for Year 10 Chemistry. For those of you that may or may not know me, my name is Ravi. I'm one of the teachers here at Elite Medics, and I'm a fourth-year medical student at UCL. Here's a little bit of my academic background. And so, yeah, a lot of you will know me because I do teach your chemistry class throughout the year. And the purpose of today's session is to kind of go through everything that I've taught you since about January onwards. So there'll be a nice little recap session. There should be fewer of you today, so you can ask me more questions and I can answer them at a more personal level as well, because there'll be less people in the chat. Hopefully you would have been sent the question packs and how to go at the questions. Those questions are an amalgamation of the questions that we've done together previously, but it helps to go through them again after you've done the content again, so that you can actually see where the key words are in the mark scheme, because a lot of chemistry, especially GCSE, is knowing what should be on the mark scheme and not. Now, again, I've got the PowerPoint today, which goes through all the topics we've done since January, including things like electrolysis, extraction of metals, separating out mixtures, and reactivity, and the different experiments involved with those. So we'll be having a look at that. There won't be any Slido today because this is a revision session, so we're not going to incorporate any Slido. However, as you know, I like to keep things quite interactive, so I will be using the chat whenever I want to ask you questions directly. And I do have a couple moderators in the back end who will be helping me to answer any of your questions, but I should be able to tend to most of your questions throughout this lesson anyway. All right, cool. So what are we actually going to start with first? We're going to look at electrolysis, just so that you guys are familiar with what I can see. I've got this masterboard here. I can see all your questions coming through, and at some point throughout the day, there will be a feedback form that will be posted in this published section. So if you would kindly fill that out, that would be great. Okay, cool. So let's make a start. Now, electrolysis, arguably one of the harder things in Year 10 chemistry. This is because it kind of incorporates a lot of concepts, including ionic compounds, right? Knowing about when an ionic compound can or cannot conduct electricity. Then looking at different substances in the different states, so either a molten, aqueous, or solid, yeah, and then stating whether or not it can conduct, and if so, what is the difference between molten and aqueous, because now in aqueous you introduce different ions, so things can get a bit more complicated. However, if you just follow the basic rules and there's an order in which we think about things, then you shouldn't get confused. Okay, so we want to be looking at the electrolysis, the molten ionic compounds, extracting metals, and aqueous solutions in this order. Okay, so again, we'll start with a brief introduction to electrolysis, and then it will get progressively harder. So what do we want to do? We want to be able to define electrolysis, a common 2 marker in the exam. You want to describe electrolysis in terms of the movement of ions. So remember, in the setup of electrolysis, we have electrons moving in the wires and ions moving in the solution, and it's the movement of the ions and electrons that helps complete the circuit. Okay. A lot of electrolysis be able to predict the products of the electrolysis reaction, and being able to do redox equations, half equations, to classify the reaction as being either oxidation or reduction. Okay, then we'll be looking at how electrolysis can be used for the metal extraction of aluminium from its ore. Okay. So this is a nice little recap. So ionic compounds, remember, these are essentially compounds formed when a metal reacts to a non-metal, and in that, the bond that is formed is an ionic bond, and this is the transfer of a pair of electrons from sorry, it's not a transfer of pairs, it's a transfer of electrons from the metal to the non-metal. As you know, metals are in group 1, 2, 3, so they'll want to lose their electrons to fill out a shell, whereas the non-metals, they're in group 6, 7, 8, and they would rather gain electrons than to lose, let's say, 5 or 6 electrons. Yeah? So you can see what's going to happen. Sodium is going to donate its electron. It's a transfer of this outer electron to the chlorine. So now both will have a full outer shell, yeah, as you can see that here. And we like to denote it. Remember how we denote it with square brackets with the charge. This is a plus, and this here will be a minus. Okay, great. Now the ionic bond is essentially a strong electrostatic force of attraction between these oppositely charged ions. Okay, this can be represented in either a ball and stick diagram, a more of a 3D diagram, or just your 2D diagram. And here are our charges. Now, with ionic compounds, we know that they will have a high melting and boiling point due to the fact that these strong electrostatic forces of attraction require lots of energy in order to break them up and overcome them. Now, when you do give that energy, the high amount of energy, it can melt. And when the ionic compounds melt, the ions are now free to move around, because essentially, when they're in that solid state, it forms this regular lattice structure, this giant lattice structure, and that fixes the ions in position, meaning they're unable to move around. And as you recall, when the factors needed for conduct electricity is you need a charge carrier that is free to move around. So we call them mobile charge carriers. So despite the fact in a solid ionic compound, despite the fact that we have charge carriers, because they're fixed in position, they're unable to move around and thus unable to carry charge. Right? Now, when you melt it, then it is free to move around. Another state is when you dissolve it in water, it's now aqueous, and again, the ions are free to move around. Hence, you've got your mobile charge carriers. Okay. But what is the difference between molten and aqueous? Essentially, molten is there's no ions from water involved, so there's no H plus and OH minus, whereas when you take the aqueous, you're introducing H plus and OH minus ions. And that becomes very crucial to when we look at the difference between, let's say, electrolysis of molten potassium bromide versus the electrolysis of aqueous potassium bromide. Two very different products are produced at the anode and cathode. Okay. Right, so the electrolyte. This is what we define as the liquid containing the ions. So this is what we're actually going to try and split apart. It could be a molten ionic substance or a dissolved ionic substance. Okay, for the reasons we just said, it needs to have mobile charge carriers. So by definition, electrolysis is a process of splitting apart an ionic compound back into its elements. For example, sodium chloride, we want to split apart into sodium and chlorine atoms. Yeah. For this, it requires an electrolyte, which is what we described as a liquid containing the ions, has to be molten or dissolved. You need your electrodes, which is going to actually connect the battery or power supply to the circuit. Then the electrodes are the solid materials that conduct electricity or attract ions towards them. The electric current, which is essentially as a result of electrons moving and also due to ions moving. Okay, so this is a setup of one with two gases. Okay, so this is where you might have a hydrogen and oxygen. Yeah. So if you do the electrolysis of water, you'll get your H plus, your OH minus, and then you'll have your hydrogen given off here and oxygen given off here. Okay. And because there's no metals involved, this electrode tends to be platinum. And here we've got the power supply and we've got our electrical wires. Now this is one where metals are involved. So if we had, let's say, I don't know, we could have the 2 graphite electrodes, and then we've got something like copper sulfate in here. And just for simplicity's sake, actually no, let's just say copper chloride for simplicity's sake. We could see that copper will get attracted to one electrode and the chloride ions will get attracted to another. And we're saying that is for molten copper chloride. Yeah. But anyway, this is the setup that you need to draw out, and I would draw out exactly like this, making sure you label one end as positive and one end as negative. Now, this is where people often get slightly confused. The cathode is the negatively charged electrode that will attract positive ions, otherwise known as cations. Okay, and the anode is the positively charged electrode that attracts negative ions, otherwise known as anions. Now, it's perfectly understandable to not be able to get your head around or get it confused in the exam. So hence why I would stay clear of using anions and cations, and as the most you should do is just say cathode and anode. And even if you can't remember that, then just say negative electrode and positive electrode. They won't dock you marks for not using the word cathode or anode. However, in the exam, if they do use the word anode or cathode, you need to be able to understand what that means. You'll need to know that the anode is the positive electrode and cathode is the negative electrode. Okay, that's crucial. Okay, good. Any questions so far? What does the VE stand for? Let me try to see what VE is. Oh, positive and negative. That's what it means. Yeah. Okay, so if you pass an electric current through the electrolyte, the free ions in the solution will end up moving towards the electrodes. And the positively charged ions will move towards the negative electrode, i.e. the cathode. And the negatively charged ions will move towards the positive electrode, i.e. the anode. And that's due to opposites attracting. Yeah. Now, when the ions reach their oppositely charged electrode, the ion will now be given off in its neutral form and return to being an element with no overall charge. So this entire process is what we call electrolysis, where we're breaking down, we're splitting up an ionic compound back to its original elements using electricity. Electrolysis. Lysis means splitting. Electro means using electrical energy. Yeah, or using, yeah. Okay, don't worry too much about this one right now. We'll get on to this in a bit. Okay, now this is interesting here. You can see that if we take an electrode that's not made of graphite, and we actually use a metal electrode. So what I didn't mention earlier was that why do we use graphite electrodes? We use graphite because it tends to be quite unreactive. Yeah. Now, if you replace the graphite electrode with something that is quite reactive, so metal, for example, what's going to happen is if the metal is at the positive electrode, it's going to start losing electrodes, because at the anode you start to it becomes oxidized, right? You start to lose electrons from the anode, and at the cathode you start to gain electrons. And what will happen is, providing this, let's say this is a copper electrode, so we'll say this is copper, and this is our copper sulfate solution here. Okay, what's going to happen is the Cu2 plus ions that are floating around in solution, they will actually get attracted to this negative electrode, right? And in doing so, you'll get copper deposits forming on this carbon cathode, right? Now, on this copper anode, because it's getting oxidized, it's losing electrons, what's going to happen is the Cu does this. Cu turns into Cu2 plus, and it's losing 2 electrons. Okay. Can you see? Cu loses 2 electrons. Cu minus 2e goes Cu2 plus, which is the same thing as, but this is the conventional way of writing it. And because that happens, you can see that this electrode starts to wither away because the copper from the electrode is now entering solution. Yeah. So, and this phenomenon is how people do electroplating. So if you wanted to coat something in silver, let's say you have a spoon and you want to silver plate it, all you would do is you'd put silver as this electrode here, and you'd be able to plate whatever you want. You put the, let's say you put the spoon as the negative electrode, and the silver as the positive electrode. You run the electrolysis and have something like silver nitrate as the electrolyte. Then what's going to happen is all the silver from the anode is going to go and deposit onto the spoon, and hence you'll get your silver plated spoon, yeah, which is quite fascinating. Yeah, we'll get onto this idea of what happens with the other sulfate ions since it's a copper sulfate solution. We'll talk about that. Now, electrolysis involves redox reactions, both reduction and oxidation reactions. So you need to remember oil rig, oxidation is the loss of electrons and reduction is the gain of electrons. If we take SO42 minus, that will turn into SO4 and will have lost 2 electrons. The copper will have gained 2 electrons to turn into Cu, just copper. So what's happening here, because it's losing electrons, this is oxidation, oxidation is loss, and because it's gaining electrons, this is reduction, reduction is gain of electrons. Okay. These are the rules here. Whenever you write a half equation, you always want to start by showing what species goes to what species. So for example, if I was going to turn chloride ions into chlorine, yeah. Let's say I had at the anode, the positive electrode, chloride ions got attracted and now going to get given off as chlorine. Remember what I need to do. I need to just show what's happening. So chloride ions turn into chlorine. Now this isn't balanced at all because there's 2 chlorines here and only 1 here. So what do I need to do? I need to make sure the number of atoms of each element must be the same on both sides. So I'm going to double this, right? Now that I've done this, the number of atoms of each element are balanced. I now need to check the charge on either side, right? There's a 2 minus here and there's 0 here. So I need to add 2 negative charges here. The best way to do that is just adding electrons, right? And now I can say that is the charge on either side the same? So here you've got 2 minus and here this is 2 minus. So yeah, it's the same. This usually 0, that's not true because it depends on whatever the half equation is. So I wouldn't worry about usually 0. Just remember the charge needs to be the same on either side. Okay. The same could be done for when I was using the copper example. Cu is going to Cu2 plus. Are the number of atoms of each element the same on either side? Yes, 1 copper, 1 copper. Now, charges, are they the same? This is 0 on the left. This is 2 plus on the right. So I need to make this 0. So how can I make this? I can either make this 2 or I can make this 0 to balance the other side. Now, there aren't any positive particles that you can just add like that, where there are negatives. So I can just add 2 electrons here. The 2 plus plus 2 minus makes 0, and that's 0. So now that's balanced as well as the charge is balanced as well. So for balancing, electrons are your best friends. Now, what the electrons doing in a half equation, it tells us if the ion is losing or gaining electrons. Okay. So just remind yourself that at the anode, at the positive electrode, the negatively charged ions that get attracted, they will lose their extra electrons, yeah, and so the reaction is now oxidized. Yeah, it's an oxidation reaction. And that makes sense because if you have a chloride ion, right? The chloride ion, if you think about what it is, a chloride ion has now 8 electrons in its outer shell, a full outer shell, but it had gained 1 electron, hence it was a negative ion. Yeah. Now, when you attract it to the anode, it's going to lose electrons to go back to its original atom form, right? And remember, chlorine has 7 electrons in its outer shell, so it needs to lose that electron, and hence that's why it was oxidized, yeah, because it's lost an electron. And similarly, at the cathode, there's reduction. So here's just another example. If your H plus is turning to hydrogen, you need to double this H plus, yeah, and then you want to balance the charge. Okay, 0 on this side, there's 2 plus on this side, so let me add 2 electrons. That makes that side 0 as well. Yeah. This is quite interesting. This is your OH minus ions. So if you do the electrolysis of water, you're going to have your OH minus attracted to the anode. Yeah. What's going to happen is OH minus turns into oxygen and water. And then if you look at the charge, you know that this is 4 minus charge. So you want to lose 4 minus charge. So you can either write it as this, or you could write it as this. 4OH, and this is the one I would do, the one that I'm writing out. 4OH minus goes to O2 plus 2H2O, okay, plus 4E minus, right? We always like to use pluses. We don't like to use minuses in equations, okay? It's neater like this. So we're saying we've lost 4 electrons, hence the 4 electrons on the other side. Okay. Okay, now I'm just going to show you something. I think this should work, but if you add up the 2 half equations, you should get the overall equation again. Okay, so for example, if I take this and this, how am I going to add them together? Well, because what you need to do is you need to make sure the number of electrons are the same. Here there's 2 and here there's 4. So I can double this to make 4. So I need to double all of this. So I'd make this as 4H plus 4E minus goes to 2H2. And then I can add this to this, because what will happen is when I add these two together, the 4E minus and the 4E minus, they will cancel because they're on opposite sides of the reaction arrow. So if I now do this, I get 4H plus 4OH minus goes on to make 2H2 plus O2 plus 2H2O. That is the overall equation for the H plus ions and the OH minus ions in the electrolysis of water. Okay. So that's quite neat, and that's something that you'll look at more at A level. So don't worry too much about this now, but it's just interesting to see how the half equations can come together. Okay, so this is the interesting thing now. I said we'll come back to this electrolysis of copper sulfate, because if we understand what ions are at play here, we have a Cu2 plus, we have the SO4 2 minus. We have, because it's solution, copper sulfate solution, we're going to have, so let me add that here, solution. We're also going to have OH minus ions, and we're going to have H plus ions, okay? So what's going to happen is Cu2 plus will go to the negative, and out of the SO4 2 minus and the OH minus will go to the positive electrode, the anode, yeah? And then what's going to happen, you're going to have your 4OH minus goes to 2H2O plus O2 plus 4E minus. Yeah, you don't need this together. Yeah. And the reason for that, the rule is in the presence of sulfate ions, OH minus is always given off as water and oxygen. So whenever there's sulfate ions present, oxygen gets given off. At the negative cathode, Cu2 plus gets attracted to the negative electrode, and that gets given off as copper. All right, we'll see more examples of this as we go through the lesson. All right, any questions? How can both the positive and negative electrode be made of the same material? Okay, interesting question. So all you have to remember is that that example, this copper sulfate example, the reason why I said that this one is a different material to this is because this one's actually going to get used up. The ions go into solution. We're introducing copper ions into solution, right? And in doing so, you're going to increase the concentration of copper ions in this solution, and thus more copper can get deposited on this negative electrode, right? But that's for the sole purpose of electroplating, or it could also be used for the purification of copper, right? I'll give you an example. If we wanted our impure copper at the anode, right? So we take all of this impure copper, so it's copper mixed with all these impurities, okay? And on this side, imagine this is all pure copper, right? So I'm going to add a, let's try and make it a nice, I don't know what we can do, but let's just make it as yellow, okay? This is all copper. This is all pure copper, all right? Right? It's nice and shiny, we'll say pure. I don't think you can see that very well, but pure copper, all right? What's going to happen is when you have your pure copper, and now you would argue that, oh, now they're both the same material, right? But essentially what's going on here is that at the anode, we always lose electrons. Oxidation is lost, right? So what's going to happen is the copper, any of the pure copper in here, remember that is your impure copper. Let me label it. So for this example, we're going to call this impure copper. Right, and now remember, don't get this confused with the electrolysis of copper sulfate. I'm just using this diagram for another purpose. Okay, so your impure copper, and what's going to happen is your copper is going to go from Cu to Cu2 plus 2E minus. So now what do we have? We have all these copper ions entering solution from this copper. Yeah. Right, and then what's going to happen is at the cathode, remember, Cu2 plus ions will get attracted to the cathode, right? So all of these Cu2 plus ions, as well as the ones that were in this solution to start off with, will now get attracted to here. And so what do you see happening? You see that you'll get more and more pure copper, so this will get longer and longer and longer, and this one will get shorter and shorter and shorter with all the impurities falling to the bottom, okay? Now, to answer your question, so this is when either they have this is for when you actually want this to wither away and you want to grow the other electrode. Now, the answer to your question about why would you use two graphite electrodes, like why are they the same material? Well, if I take us back to this setup, okay, I said these are both graphite or carbon electrodes, okay? And you know what? Let's just make this a copper sulfate solution. So we're not changing the electrolyte. We're making this copper sulfate solution. Okay. Now, carbon, yeah, these carbon graphite electrodes, these are unreactive. Okay. They're unreactive because that's just how they are. All right. They're unreactive. And for that reason, well, they're firstly they're unreactive and they're able to conduct electricity. Okay, and now we know why graphite is able to conduct electricity. If you cast your mind back to structure and bonding, if you look at what graphite actually looks like, it's these hexagonal rings, yeah, that are kind of joined up. Okay, you get the idea. And each carbon is joined to three other carbons, meaning that there's one electron delocalized for every carbon. Yeah. And it's those delocalized electrons that are free to move around and conduct electricity. Okay. So, but why do we use these? So firstly, they're good electrical conductors. Secondly, they're unreactive, meaning they will not react with the solution, and they're unlikely to lose or gain electrons themselves. Okay, so the carbon actually won't become reduced or oxidized. Only the ions that get attracted to the carbon electrodes, they will get oxidized and reduced. Okay. And can you see how that's different to the example we were looking at just here, where the actual anode itself will get withered away due to the purification of copper, or if you're electroplating the cathode. Make sense? How could both? Yeah, okay, we did that one. Fine. Are cations and anions just general terms for charged ions? So yeah, okay, yeah, they're general terms, but cations are your ions to get attracted to the cathode, hence they are positively charged. Yeah, and anions are your ions that get attracted to the anode, hence they are negatively charged. Right. Right. Okay, we'll have a look at some of these later. Yeah, these calculation questions we'll try. Okay, we've got a question here. Why does copper get released instead of hydrogen? Very good question. And we're going to get onto that. That's one of the rules that is coming up. But essentially, any metal that is less reactive than hydrogen is going to get released at the cathode. And the reason for that is the more reactive out of the metal or hydrogen is going to want to stay in solution, react with the other ions in solution. Yeah. So because copper is less reactive than hydrogen, copper is lower down than hydrogen in the reactivity series, it is going to get released at the cathode. And that's great. People are asking what happens to the H plus in the copper sulfate solution. Well, the H plus will react with the SO4 minus, because that's what didn't get go to the anode, and then you'll get another byproduct there. Okay, but you don't need to worry too much about the example for copper sulfate. We'll look at that for brine, the electrolysis of brine, which is sodium chloride solution. You're right. Okay, I'm getting more questions about why does the anode look like it's broken down and corroded. So again, this is an example that is probably unlikely to come up in your exam as a standard electrolysis setup. Okay, because this isn't a standard. This is only if you're trying to purify copper or you're trying to electroplate. The standard setup is the one where you use both electrodes being made of carbon, right? Now, I'll explain again why this is actually withering away. So for that, let me just whip out the other one. Okay, so the reason why it's withering away, so we said, let's imagine this is your impure copper. So you know what, let's make it even clearer. Let's put all of these impurities in this copper. So you can see there's copper as well as there's all these impurities, okay? All right. Now, what's going to happen is, at the anode, think back to basics. At the anode, what happens? Oxidation occurs and you lose electrons. So whatever's at the anode, yeah, that is going to lose electrons. So not only is the OH minus going to react and lose electrons, but also because the copper electrode itself is reactive, it's not carbon, it's not unreactive. Because it itself is also a metal that reacts, yeah, you're going to have the copper coming out of the electrode and entering solution because you're losing electrons. Okay. Now, as that happens, these copper ions now enter solution. All right. And once they've entered solution, now you've got an abundance of these copper ions that are now going to get attracted to this negative electrode, the cathode. And in doing so, we know at the cathode, reduction occurs where they gain electrons. So this Cu2 plus ions they will gain electrons and be converted to copper, right? And that copper will be pure copper that will deposit. Yeah, deposit means to add on to the original copper electrode, the pure copper electrode, and thus this will get longer and this one will get shorter, and all your impurities will fall to the bottom. Okay, does that make sense? If it's still not making as much sense, don't worry too much about this one, because this is a special case one. And worst, I don't think they'll have, if you're unlucky, they might have one question about this, but the more likely question they'll have is regarding just your normal electrolysis of a molten substance or of a aqueous solution. Okay. Cool. Right. All right. So let's have a look at this question here. The diagram shows apparatus used by a student to investigate electrolysis. The student was given a solution by the teacher. The solution contained a mixture of ionic compounds. Name the particles which carry the electric current through the metal wires. It's going to be your electrons. The solution is going to be your ions. Okay. Let me use a red pen so it stands out. Right, then, which element is most likely to be formed at the negative electrode? So, at the negative electrode, one is out of these positive ions, isn't it? Now, it's all about which is the least reactive metal ion. That is the one, or the least reactive ion is going to get attracted to the cathode, right? So which one is the least reactive? Well, if you look at reactivity series, you'll see that copper is the least reactive, and hence copper will be formed at the cathode. Yeah. So you can see, because they are positive ions, and copper is the least reactive. Yeah. And why did I say the least reactive gets formed at the cathode? Because the more reactive ones, they want to stay in solution and react with the other ions. Yeah. Okay, so the electrolysis of sodium chloride solution is an industrial process. The reaction of one of the electrodes can be represented by the equation shown below, whereby here the chloride ions are oxidized. Yeah, you can see why, because it's losing 2 electrons. So Cl minus loses electrons. Okay, that's simple. Now you want to do the one for the other electrode. So for sodium chloride, now we're going to explain. So I've already told you why H plus gets attracted to the cathode over sodium, because sodium is a very reactive metal, and thus the H plus is going to get given off instead of the sodium. Yeah, because the sodium wants to stay in solution. So notice you go H plus to H2, you need 2 of these H pluses, and you also need 2 electrons. Yeah, to balance the charge, 0 and 0. Okay, so let's look at these molten ionic compounds. These are much easier than any of the examples we've looked at, because there's only 2 ions involved. Okay, let's take molten lead bromide, for example. Okay, essentially, molten lead bromide is going to get split up into lead and bromine, right? Because they're the only 2 ions. You don't have your H plus ions and hydroxide ions present, because it's not solution. This is molten. It's just melted solid. Yeah. So if we look at what happens here, so for those of you again asking that question about why can we use the same material for the electrodes, because here the electrodes aren't actually going to react. It's these ions that are going to react. Yeah. However, if we made this electrode, if we made this a lead electrode, then yeah, this is going to start getting withered away, and it's going to start it's going to start depositing onto this negative electrode. So very important, you don't use a metal, and imagine if you didn't even use lead, imagine you use something like I don't know, sodium, a sodium electrode, you're going to start introducing other ions and you're going to mess everything up. So in order to make things simple, we use unreactive graphite electrodes, carbon electrodes, that will not react with the other ions. Yeah. Okay, cool. So let's have a look at what's going on. So we have our molten lead bromide. Okay. Then we have our negative electrode, the cathode, and our positive electrode, the anode. What ions do we have present? We have positive Pb2 plus ions. Now remember, this is one of those you just need to remember. If you look in the periodic table, you'll find lead, but it won't be in group 1 or 2 or 3 or 4 or 5. It's in the transition element group. And that's just one you have to remember is Pb2 plus. Okay. Now, these positive ions, they get attracted to the cathode, and the Br minus ions, they will obviously get attracted to the positive electrode, the anode. Okay. Right, so let's have a look at what's going to happen in terms of half equations. Yeah, so when the electricity is turned on, the lead ions will go to the cathode, and the bromide ions will go towards the anode, and the movement of them will carry the current. So let's have a look at this. So the Br minus ions move to the positive anode where they lose electrons and become oxidized. So let's see what's going on. Br minus is going to turn into bromine gas. Okay, that's how I start it. I know bromine is going to be diatomic. You have to make sure, if you only put Br, you're going to get it wrong. You have to put Br2. Then you can balance it and say, okay, I need 2 Br minuses. And then 2 minus that side, so I need 2 minuses on this side, okay? Great. So, because this is losing 2 electrons, I know this is oxidation, yeah? Then at the other electrode, now notice how they've written it. They put minus 2 minus. That's not the conventional way, but it's technically the same thing because plus 2 minus on one side becomes minus 2 minus on the other side. But I wouldn't write it like that. I would write it the way I have, which is plus 2 minus on this side. Okay, then let's look at what happens at the cathode. Well, the Pb2 plus ions, they're going to gain 2 electrons to form lead because you're balancing the charge. And yeah, that's how you get your pure lead. Okay, any questions? Still a bit confused on why the sulfate does not get released in the copper sulfate solution. It's just one of the rules you need to know, that over sulfate, it's the hydroxide ion that gets attracted to the positive electrode, and for that reason, that will give off the oxygen. Yeah, it's just one of the rules you need to know. Okay. And there'll be another such rule when we look at the halides. You'll see that the halide is usually given off because we assume it is a concentrated halide solution. Okay. And again, that's just something you need to know. There's no reasoning behind it that you need to be aware of at your stage. Okay. Breaks, yeah, good question. When will break will be in 5 minutes or so. Okay. Where do I get the Br2 from? Well, the Br2 is because I don't get it from anywhere. I just understand that bromine, when bromine in its standard state, yeah, has to be a gas that is diatomic, because bromine atoms, you'll remember we looked at this in group 7. We said that bromine atoms, they have 7 electrons in the outer shell. Okay. Now, atoms like to be stable. And with 7 electrons in its outer shell, it's not very stable. It's quite reactive. So what it will do is it will grab a buddy and it will get another bromine, and they will share that 7th electron. And now they'll both have 8 electrons in their outer shell. Okay. And now because they have a stable outer shells, they'll be stable, and that's what they like to be. So hence why bromine is diatomic, chlorine diatomic, iodine diatomic, nitrogen diatomic, oxygen diatomic. A lot of the gases that are non-metals are diatomic at room temperature, yeah? Or diatomic in their natural state. Yes, that's why I just was answering. How do we know when something's diatomic? Because usually a non-metal by itself is unlikely. Things like carbon and sulfur, they're quite stable. They don't need to be like, that's why they don't react as much, because they're quite stable. 4 electrons in the outer shell. Yeah, they're neither going to gain 4 electrons nor they're going to lose 4 electrons. They're happy just to sit around with 4 electrons in the outer shell. Okay. But things like nitrogen, which has 5 electrons in the outer shell, would rather it would rather buddy up. So let's see, nitrogen, 5 electrons in its outer shell, right? So you're gonna have like that, and then you'll have 1, 2, 3, 4. Actually, I believe nitrogen is a double bond, so let's do that properly. So nitrogen, cross dot, cross dot. So that's 2. You need 1, 2, 3. Actually, nitrogen might even be a triple bond. Let me just double check. Yeah, triple bond, that's what I was thinking. So instead, we're going to do this. We'll add another cross and a dot here. So there's 3 pairs of electrons here. So 1, 2, 3, 4, 5, and then 1, 2. I think you can't do that one. But... Okay, so you can see it's diatomic. It's got, now why do I know this is correct? Because there's 6 electrons in the middle, 1, 2, 3, 4, 5, 6, and then 2, 7, 8. So there's 8 around this nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. So 8 around this nitrogen. Okay, that's the key thing. They want to have a full outer shell around each atom. Okay. The same can be said for oxygen. I'll show you that one quickly as well, because just for understanding. So oxygen. Okay, so I believe that will have 1, 2. There's 6 electrons in the outer shell of oxygen. 2. 6. And then this will be 1, 2, 3, 4, 5, 6. Okay. This will probably be a double bond, isn't it? So we'll add this into the center. Okay. So as you can see now, there's a double bond. They're sharing 2 pairs of electrons. So you've got 1, 2, 3, 4, 5, 6 contributed from this oxygen, and 6 contributed from this oxygen. But because now you're sharing 2 electrons from the other oxygen, you've got 4 plus 4, that's 8 around this oxygen. 4 plus 4, 8 around this oxygen. Yeah? And you can see that if you look at oxygen, it's diatomic, and it should have a double bond in between it. Yeah, can you see that? Double bond there. Yeah, that's just showing you why these are diatomic, because it likes to have a full outer shell around each atom. Yeah, and the best way to do it is just grab a buddy, right? Share with your buddy like that. Yeah. All right, cool. Any other questions? My teacher told me that there is a rule for diatomic nonmetals. It looks like a 7 from the nitrogen and all of group 7. Let's have a look. See, there are these little ways of remembering things, but I genuinely like to just... Where is the 7? Oh, right. You mean like this? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Yeah, I guess. Yeah, makes sense. But also hydrogen is diatomic as well, so you don't want to miss that one out. Yeah, I mean, if you want to remember like that, so from nitrogen onwards, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, these are all diatomic, and so is hydrogen. They're the main ones that I think you need to remember. All of group 8 will be, they're not diatomic, even though they're non-metals, because they have a full outer shell anyway. Carbon is pretty stable by itself, so it doesn't need to do that. Sulfur, again, is also pretty stable. It doesn't really need to be diatomic. Okay. All right, good. Let's move on. Any other questions? Yeah, so how do we figure out the amount of bonds and elements? So you saw me just do it. You can see it. If you don't remember them, you kind of have to work them out. So did you see what I did there? I literally showed you live how I figured out that it was a double bond instead of, and same I did for nitrogen. I was like,